Hello everyone, welcome to this webinar. My name is Alok Singh Tomar and today I will talk about chemistry base and its Midas FEA analysis. So let's begin. Agenda of this presentation will be I will discuss about chemistry base, brief history and its advantages and a comparison with other bridges in terms of general characteristic, and I will also discuss about details related to structural component of chemistry base. Then there will be some example about iconic chemistry base in the border, and then I will discuss about case study iconic shell base. I will also talk about longitudinal analysis, transverse analysis, local anchorage analysis in Midas Civil. And then if you have any questions, we can discuss about that one as well. Let us, this is about me, myself Alok Tomar. I'm a member of Institute of Engineers India. I have graduated with BTech MTech degree in civil engineering from IIT Kanpur in year 2010. And I have 14 years of experience in analysis and design of civil infrastructures. I work with various projects related to bridges, airport, arenas, small special structures, temporary works, offshore structures. I'm also involved in project E45 New Overpass, Tea Bridges, Denmark, Mumbai Metro Cable Shed, Iconic Shun Bridge, RA256 South Sura Road Bridge, Doha Link, Hong Kong Airport, Abu Dhabi Midfield Terminal Airport, Dubai Mall Extensions, Etihad Arena, Mother Grade Expo 2020, Al Naga Corridor, One Jabil, Amachan, and Jodica project. I worked with Larsen Tubro for 2 years, then also worked with Technipat India in Mumbai. Then I also worked with Tony Jane Partners more than 10 years in Abu Dhabi. Presently, I'm working with Rambol India as a lead engineer, business civil. I'm also a founder and contributor online learning platform, scaleupmyskill.com, and I have a hobbies of sketching, animations, SketchUp, and blogging. Let's discuss the introduction of chemistry base. So basically, the chemistry base are inspired from the Egyptian sailing ships. They are also evolved from the suspension bridge. Early Chinese people, they used to use cave state system to construct suspension bridges. In 16th century, Croatian polymath Fossil Virangio do first proposal of chemistry bridge. You see here. So the load path of chemistry bridge is like it is a chemistry bridge is itself a indeterminate structures. Here the deck load is transferred to the cable and then it goes to the pylon, and then pylon, from pylon it goes to the foundation. So here the steel cables are subjected to tension, deck is subjected to compression and bending, and pylon is also subjected to highly compression and sometimes bending as well. Here the tension of steel cable and its inclination is related with respect to how much tubular weight it is carrying. So you see the tension of the steel cable is W upon sine theta, where W is the tributary weight or vertical loading that it is going to support, and theta is its inclination. There are various advantages of cable sheet bridge over other kind of bridges of similar span. The first advantage is structural efficiency. The structure is self-anchored structure, so it is having better load distribution and material efficiency. Aesthetic appeal is also very good in chemistry base as compared to other base. It looks more modern and elegant design and represents the culture of that particular city. Economic considerations are also bright for chemistry base. It's cost effective, less time construction than suspension base. In cable stayed base, various kind of structures can be formed, so it has a very good versatility and adaptability. Span length, medium to longer bridge, versatile for different crossing over river, valleys, highways, foundation, requirement from deep well foundation to shallow foundation. In terms of maintenance and durability, reduced maintenance as compared to suspension base, and also it can withstand hard environment conditions. And in terms of engineering and design flexibility, various design possible including single pylon, multi-pylon, fan arrangement provide various choice to engineers suited for specific site conditions, and traffic and load handling is much better as compared to other bridges. This slide presents the general characteristic of various bridges including PSC box girder bridge, extra doors bridges, cable stayed bridge, and cable suspension bridge. So let's go one by one. So for PSC box girder bridges, they are applicable span length for these kind of bridges are from 40 meter to 200 meter using balance cantilever method. On the deck depth for box girder bridges are L by 16 to L by 20 at support and L by 30 to L by 40 at mid span. It doesn't require pylon height and it is not sensitive towards wind. The stress limit for tendons for box girder bridge is 0.7 FPU. However, for extra dose bridges, which are applicable for 80 meter to 250 meter, their deck depth is smaller than the box girder bridges. In extra dose bridges, the deck depth is L by 30 to L by 40 at support and L by 40 to L by 50 at midspan. Pylon height from deck for extra dose bridge is L by 8 to L by 15 and wind sensitivity is negligible. However, here the stress limit for stay cables is limited to 0.6 FPU. Now, as compared to extra dose bridge, the cable stayed base have economic span from 80 meter to 600 meter. Here the deck depth is kind of very less as compared to extra dose bridge, and it can make it uniform throughout the span from 2 meter to 3 meter. Pylon height from deck for cable bridge is L by 3 to L by 5, and it is very sensitive to wind, so we need to check the wind as well for the deck. And stress limit for cables is limited to 0.45 FPU. And for cable suspension base, the applicable span is ranging from 500 meter to 1400 meter. Here the deck depth is very small as compared to even cable stayed base. It is 1 meter to 2 meter only. And pylon height from deck is L by 9, which is again lesser than the cable stayed base. Wind sensitivity is very high and stress limit for cable is 0.45 FPU. Here FPU is the ultimate tensile strength of the cables. This slide presents the structural component of cable stayed base. So as you see, this is the tower, also called pylon, and this is the major component used for transferring the compression force to the foundation. The second component is the stay cables, which are tension only elements, and deck is this one, which is supporting the roadways and vehicle and pedestrians traffic, and the fourth component is the foundation. The deck has also a stitch segment which is at the middle of main span. This is the back span of the deck, and this is the main span, and this is another back span. First structural component of cable stayed base is tower. Tower supports cable. It has a cross beam which supports the deck. Uh, the use of tower is it is transferring the compression load to the foundation. So, and the shape of tower affects the torsional rigidity of cables. So it can be single one tower or twin towers. S shape, A shape, inclined towers. So various shape of towers can be found in cable stayed base. Another structural component are cables, and cables are basically four types: parallel bar cables, locked coil strand cables, parallel wire cables, and parallel strand cables. In parallel bar cables, the steel rods or bars are parallel to each other and they are basically encapsulated into a metal duct, and grout is filled in between. And the locked coil strand cables, they are basically two layers of cables. Inside layer is helically twisted wires, round shape, and the outside layer is having Z or S shaped wires. Again, they are also helically twisted, and this kind of cable have higher modulus of elasticity and better resistance to corrosion. The third type, parallel wire cables, has 7 mm parallel wires arranged in hexagonal shape, and since there is no twisting of this cable, they have better strength and stiffness, and there is a very small wide ratio which help them to prevent corrosions. And the fourth type of cable is parallel strand cables, which is another variation of parallel wire cables, but here the instead of wires, the pre-stressing strands are there. And cable arrangement in longitude direction also have three types. They have a harp type, fan type, and radial type. In harp type, the stray cables are having constant inclination. However, in fan type, the inclination varies, and but there is a uniform spacing at anchorage location of pylon. However, in radial type, all cables are radiated from one point of the pylon. Based on the cable arrangement in transverse direction, there are basically two type of system. First, a single plane system. In single plane system, the system composed of single plane cable layout in longitudinal direction of cables. So here the main girder must have adequate torsional stiffness to resist the torsional forces. In that side, you see the photograph of Hudayrat Island Bridge, which has a single plane system. In double plane system, the stay cables have two plane cable layout, and here the tower should have either two plane vertical system or two plane incline systems. Here anchors of stay cable located either outside of the deck structure or inside of main girder. Uh, the right side photograph is for Pathala bridge, which has a double plane system. This slide presents the different anchorage arrangement of cables in deck. So the cable in deck looks like this. You see here. So in this portion, this is the bearing plate here, and there is a anchor head, and deck stressing beam or deck diaphragm where it is supported will be somewhere here, and it is also having a guide deviator at this location and a VP pipe, which is anti-vandalism pipe, installed at this location. This is to prevent any damage to the stay cable due to human mischievous activities. And then this end of stay cable connected to pylon. These are the various arrangement of anchors uh, of stay cables based on normal stay cables or cables with dampers or cable with fire protection or cable with damper and fire protections presented. This is the AVP details. This is the anchorage arrangement of cable in pylon region. So the arrangement of the steel pipe is same as previous, which we have shown in anchorage in the deck. However, here you see the inside pylon. There are various arrangement, whether it is inside arrangement or whether it is overlapped arrangement or outside steel bracket and link arrangement or arrangement using a saddle or clevis type. This is the another main component of cable sheet base, the deck. The deck shape varies based on its requirement for flexural and torsional rigidity and its carriageway width and whether it is sensitive towards wind or not. Based on that, the shape and size of the deck determined. Usually the depth of the deck is 2 meter to 3 meter, and there are various arrangement of the deck as you see here. Sensitivity for wind vibration depends on the proportion size of the deck. So based on the past studies, if the width of deck is greater than 10 times depth of the deck, and also if it is greater than span length L divided by 30, then it is considered to be safe against wind vibration. And if these condition does not meet, then the deck require wind nose, as you see here, for the case where the width is lesser than 10 times height. And if there is a width lesser than L by 30, then it also require a shaped tower with additional torsional rigidity against vibration. This is one example of iconic cable sheet bridge. The bridge name is Rusky Bridge, Russia, and it has a longest span cable sheet bridge of the world. With maximum length of the main span is 1104 meter, and the maximum height of pylon is 324 meter, and total length of the bridge is 1885 meter. Let us discuss the case study for today, iconic Shunya bridge. So iconic Shunya bridge has pylon shape of 0. So this magenta color shown here is a steel pylon. This is shape of 0, and it is basically 130-meter long with 80-meter main span and 50-meter back span. The main span is crossing the Wakola Nala crossing. It's a river structure, and the back span is over the existing road here. And here this is a part of Mumbai Metro Line 2B project, and here the client is MMRDA, contractor is J Kumar Infra Projects, and general consultant is ICA Consortium GC, and design detailed design consultant is Design Fact India Private Limited, and structural consultant is Tony G and Partners. So, and project location is Mumbai. Geometric details of iconic Shuni Bridge. Iconic Shuni Bridge has pylon with the shape of zero. It is representing India's contribution to mathematics. So that's why this is going to be a very iconic structure in Mumbai. The main span of this bridge is 80 meter, and back span is 50 meter with total length of 130 meter. The height of pylon from rail top is 28.7 meter with height to length ratio is 4.5, and it has two plain cables. There are total of 10 pair of stay cables, where 6 pairs are used in main span and 4 pairs are used in back span. Main span of deck has 24 deck segments. This is the elevation and top view of longitudinal model of bi-connection bridge. So the pylon is in shape of 0 as you see here, and the pylon tower have center to center distance of 13.65 meter, Total height 28.7 from the deck top level, and the width of the deck is 12.9 meter. The spacing of cable at main span is 9.1 meter, and and at back span the spacing between the cable is 7.5 meter. Cable spacing at pylon is 2 meter. This slide presents the deck concrete outline. So this is the main span and this is the back span. In the main span, there are basically 6 trussing beam as you see here, and there are blisters which are shown here. And in the back span, there are 5 trussing beams as shown here. This is the stitching beam portion of the deck, which is 300 mm wide, and 3 segments of the deck are erected on false work, and remaining 21 segments of main span they are erected using balanced cantilever method. And some portion of the deck near to the pylon, which is cast sensitive on false work as shown here, and remaining portion of the back span is segmental cast precast segments with varying length from 2.2 meter to 3 meter, and the depth of the deck is 3 meter. Typical deck section looks like this with varying thickness of the bottom slab based on the location as you see here. And there is a stressing beam at few segments as you see here, where the stressing beam is provided at the top of the deck. This is the global model of Schoner bridge used for longitudinal analysis. It comprises adjacent span, west approach, and the east approach, along with the cable straight portion of the bridge. The west approach is having deck, which is a steel concrete composite deck with the grillage type of structures, and the east approach is having a U-trough girder. This is the elevation view of global model. So here as you see, this is the west approach and this is the east approach. West approach is having a span length of 43.5 meter, while east approach is 29 meter. The total height of pylon from the top of the deck is 28.7 meter. As you see here, the cable spacing at main span is 9.1 meter, while the cable spacing at the back span is 7.5 meter. The cable spacing at pylon is 2 meter, and the angle of each cable in main span varies from 18 degree to 31 degree, while in back span the angle varies from 24 degree to 34 degree. This slide presents the modeling strategy of longitudinal global model of iconic Schonbridge. Here, stick cable, as you see, is a model as a tension only elements. They are connected to the deck element using a rigid link. Deck element is having section size similar to each segment details of the deck, and there are 2 lines as you see parallel to the deck center line. They are representing the dummy elements, and the these dummy elements are basically the center line of the tracks. And this portion, which is the west approach of the Sony bridge, that is modeled as a grillage beam elements for steel concrete composite deck, and the piles are also modeled as a line element with provided lateral spring stiffness at each nodes, and there is a vertical spring provided at the end of pile representing the pile end bearing. And the details related to bearing are shown like this, which will be discussed in the next slide. And Each approach representing the two U-trough girder, they are modeled as a line beam element as shown here. And there is a pile group stiffness provided at this column. This slide presents the bearing details and its modeling. So as you see here, the detail 2 P477. This is the detail related to the bearing at pylon location. So there is a one fixed bearing here, and one is transverse guided bearing at this location, and this is connected to the deck node using a rigid links like this. And these are the detail 1 and detail 3 are bearing details and its connection to the adjacent slab and adjacent deck location. So basically this is a pier head, and there are basically one side of west approach there are four type of bearing. So one is longitudinally guided and three are pod bearing. The other side of portion where the cable straight portion of the bridge is there are two bearing. One is longitudinal guided bearing and another is free bearing. Same way, each approach is also having one free bearing and one longitudinal guided bearing. And there is a seismic restrainer also model, which is having stiffness as per the type of product in X and Y direction. The seismic restrainer is provided here. And this way, the pier head is connected to the common pier using rigid links here and here. This presents the material properties used in the global model. So the concrete grade for piers, pile cap and piles considered in the model is 40 MPa, that is a cube compressive strength. And for deck, the concrete grade considered is 60 MPa cube strength. And there are 70% humidity considered for time dependent effect, and the code used for creep and shrinkage is CVB FIP model code 2010. The pre-stressing steel strand properties is considered as a nominal diameter of 15.2 mm with a nominal area strand of 140 mm square with ultimate yield strength of 1860 MPa. Steel reinforcement grade considered in the design is 500D as per IS 1786, and the structure steel considered in pylon is 350 MPa. The stay cables strands dia considered is 15.7 mm, and nominal area strand is considered 150 mm. This is the basic loading of longitudinal global model. So self-weight is applied using a self-weight tool of Midas civil, and it takes the property of material whatever is defined, and it calculates the self-weight. The creep and shrinkage functions are also inputted in the Midas civil based on CBFIB to 2010 code, and tendon properties is also defined like this. Diaphragm load and blister load are applied as a point load as shown here. Dead load due to cable stretching beam are applied as a point load at both the end of the deck, and handrail loads is applied as a UDL in both the side of the deck. Steel parapets, rails, pads and plinth load are applied on deck as a UDL as shown here. Miscellaneous load and cables, cable trays and cable trough load are also applied as a UDL as shown here. This is the PT layout of bridge deck. So left side is top tendons. So basically these are cantilever tendons as model, And these are the bottom tendon of the deck, which are a continuity tendon as model here. Cable initial pretensions are determined using unknown load factor and cable tuning option of Midas Civil. And then backward analysis is performed to evaluate the pretension at each construction stage, and then to account for creep and sink case effect also in the cable tuning. A forward construction analysis is performed, and this way the final tuned stay cable tension forces are determined. This is the final pretension of stay cable as shown here, and the stressing of stay cables are in two stages. Live load on the bridge is shown here, and this is basically one car load. So one car is having total axle load of 17 tons. The configuration of this car is basically two types as per the IRIS code. So this is applied in Midas civil model, and since the bridge is having a curvature of 352 meter, so a centrifugal force is also applied as shown here. Centrifugal forces are applied for one track, two track based on different critical conditions. Braking and traction are also applied as per the IRS code. The traction is 20% of the vertical axle load, and the braking is 18% of the vertical axle load. The dynamic allowance factor for live load in longitudinal analysis considered is 1.3, and for transverse analysis it is considered 2.0. For wind load calculation, the IRS bridge rules 2.11.2 followed. Wind load is calculated for basic two conditions: the wind load on structure on loaded bridge condition, where the wind speed considered is 117.5 km per hour, and for unloaded bridge condition, the wind speed considered is 158 km per hour. The various angle of wind are taken from 0 to 90 degree with interval of 10 degree, and all the wind load cases are enveloped and used in the design combinations. Differential settlement of 12 mm is considered in the bridge. This slide presents the temperature loading on the bridge. So the bridge with concrete elements, they were provided with the uniform temperature of plus 27.4 degree and minus 27.4 degree in separate case. For pylon structures, the maximum temperature uniform temperature considered was 42.4 degree, and minimum temperature considered is minus 37.4 degrees Celsius. Stake cables also have a different variations as per the IRS code. So there's a variation of temperature of 10 degree considered for stake cables and the deck, and similarly the same variation also considered for stake cable and the pylon, and stake cables of left side of the pylon versus the right side of the pylon are also considered. The temperature gradient based on the thickness of the deck are evaluated and applied in the Midas civil as shown here. Bearing friction of the bridge is considered 10% of permanent reaction in expansion as well as in contraction. Seismic load on bridge deck is evaluated using elastic response spectrum method as per IS 1893 part 1, and response modification factor of 1 and importance factor of 1.5, and the seismic zone 3 is taken, and the soil condition type 2 is considered, and based on that the design horizontal seismic coefficient is evaluated, and that was inputted in Midas civil, which is shown here. And this is basically being used in the model, and then based on design of various other structural component, and since there is a different modification factor for superstructure and RCPs and steel pylon, So superstructure, the modification factor is 2, and RCPS, the modification factor is 3. So these have been taken care in load combination while extracting the design forces. These are the design load combination which have been considered in design of various component of braces. This is as per IRS code, and there are some additional load cases for seismic conditions are also added as shown here, which is as per IRS seismic code 2020, and based on that all design load combinations are formed in Midas Civil, which is used for design of components. After performing the ULS analysis, this is the ultimate longitudinal bending moment of the deck and pylon. This is the ultimate longitudinal moment in MZ direction for the deck and also for the pylon. This is the ultimate axial force envelope for the deck and also for the pylon, and ultimate shear envelope for the deck and pylon. Stresses check are done using these clauses as per IRS concrete code. So for SLS1 case, stresses of the deck are checked and is found to be all under compression because there is no tension stress allowed at that location. For SLS1 to SLS5 case, the compressive stress is limited to zero point 0.4 FCK, and pre-stress at transverse location, the stresses in pre-stress tendon is limited to zero point 0.7 FPU, and at jacking force is limited to zero point 0.8 FPU. For construction stage analysis, the stresses are limited to zero point 0.4 FCK for compressive stress, and tensile stress of concrete is limited to 1 MPa for cast sensitive portion. This is the deck stress at SLS1 case. So as you see here, all are under compression and within that limit. This is another stress diagram for deck for SLS envelope cases. Here deck stress is checked for maximum compressive stress and it is found to be within that limit. This is the SLS envelope of stay cable stresses. So all stresses and stay cables are within 0.45 FPU. Let's discuss the transverse design analysis model. So transverse design was carried out using two modules. One model is for main span, as you see here, and another is model for back span. For main span and back span, the strategy is same. The plate element are modeled as a plate element, and wherever the stressing beam are present and the diaphragm is present, that is modeled as a solid element, and the location where the stay cable is going to be anchored, that location is supported with vertical spring stiffness, and the stiffness of those location is evaluated in a separate model using a unit load method, where a unit load is applied at the location of cable anchorage, and the deflection of the deck at that particular node is determined, and based on that the stiffness is evaluated. That vertical spring stiffness is provided at these anchorage point, and the horizontal component of the stay cable in ULS and SLS case are applied as a point load, and that is determined through the global model that we discussed previously. And this way the analysis of this transverse design is done, and then various component of the deck forces are extracted and used for the design. Similar to global model, here also in transverse model, load due to PT plaster, handrails, miscellaneous rail pads and plane are applied. Steel parapets and stickable forces are applied as here, shown here. Various position of crane load as a point load as shown here are applied on the deck, and all the critical locations are considered, and the envelope of that is used in design load combinations. Extreme cases of derailment loads are also considered in transverse design as seen here. Second extreme cases are cable loss case, which are also considered as shown here. Here the dynamic factor for cable loss is considered to be 2.0, and how this cable loss force is applied, let me explain. First, the support corresponding to the cable which is going to be lost is removed, and whatever is the previous support reaction, that is multiplied with a factor of 2 and applied in reverse direction, and this way the cable loss case are generated for each cable anchor location of each braces, and based on that the critical design load envelope is used for the design. These are the critical ULS moments and shear forces of the deck elements. Those are extracted from the analysis model. Similarly, critical ULS forces for middle top slab and bottom slab as well. Design of stressing beam is done using a transverse model, converting that transverse model into a simplified version with converting the solid element of stressing beam into a line element, so that it will be easy for us to extract the design forces, and we can utilize that directly for the design. And here you see this is the beam span of the transverse model, and this is the back span. So here you see instead of solid element, now we are using a line element for the stressing beam, and this line element is connected to the neighboring plate element of the deck using rigid links, elastic rigid links as you see here, and rest of the detail are same as previous discussed in transverse design. These are the ULS, CLS and SLS design loads of stressing beam extracted from stressing beam model. This slide presents the FEA model for Anchorage design in Midas FEA Annex. So a portion of bridge deck is modeled in FEA Annex as a 3D element, and here another side of the bridge deck is restrained in X, Y and Z direction, and anchorage side there is a pressure due to the anchorage of tendon is applied as a pressure load here, and then stresses are determined, and this is the stresses from the FEA model. Once the stresses we receive, we found the stresses, then these stresses are converted into tensile forces in longitudinal and transverse direction, and based on that the reinforcement requirement in anchorage face and far face of the anchorage and equilibrium reinforcement is determined. So this is for anchorage. This is the another pier head segment of deck with the anchorage, and the similar principle is applied here as well, and anchorage reinforcement and the equilibrium reinforcement are evaluated based on this stress contour. This is the 3D FEA model of deck with blister location. So same approach is followed here as well, and the required reinforcement is evaluated. This is for stressing beam segment. So here also the required reinforcement is evaluated using 3D FEA annex. This is the total requirement is determined in transverse direction of the deck which is a combination of transverse flexure, longitudinal and shear torsion requirement, and anchorage and equilibrium reinforcement requirement at different segments. So based on this finding, the detailed design of deck is performed. This conclude my presentation. Thank you very much for listening me patiently, and please feel free to contact me at my email ID alokstiitk@gmail.com for any questions or query related to this. Thank you very much.